scientist. And the first point, and therefore I just actually wanted, this was perhaps the most important point I would like to show that picture, is so we had some private conversations, David, Amanda, and I, about a lot of questions, matter and science, science and mysticism, and also the question, what is real, what is reality? And the first question I would like to ask in my talk is Plato's mathematical world real? And I don't define what real means in that sense. Yeah, perhaps postulate that. And the picture, what you see here, is a so-called Mandelbrot set. It's something which is of enormous complexity, but it has a very simple formula to construct that. So this is something which you do a simple transformation on a plane of complex numbers, and you get those beautiful pictures. And what I will argue is this something which just scientists develop, or is this also something which has been always there? In a certain moment we encounter that. Going back, I just talked about ancient cultures, and I would like to talk about math. So some kind of mathematical theory, some kind of mathematical truths have been found in a lot of ancient cultures. So we have the Egyptians, we have the Babylonians, and they already dealt with what we call first forms of math. But the real breakthrough, and I think this is what we can perhaps now can say 2,500 years of scientific culture, has been the Greeks. One important name has been already mentioned, that was Pythagoras of Samos. The other important person is Thales of Miletus. And both persons did something which was a real huge breakthrough, something completely new, and that is finding a mathematical proof. So they not just played around with mathematical relations, with mathematical theories, they really started what is the fundament of modern science. And that is finding an impeccable argument using only the methods of pure logical reasoning, and which enables one to infer the validity of given mathematical assertions from the pre-established validity of other mathematical assertions. This is what we call theorems, word you mentioned before, or from particular primitive assertions, which we call axioms. And the validity of those axioms is taken to be self-evident. This is, of course, something you can criticize, but this is where everything built up. You start with your axioms, you build your theorems, and you build up more and more theorems, so you have really something which is a rock-solid fundament, and you can really build certain cathedrals out of that. That was breakthrough number one, the concept of mathematical proofs and working only with pure logical reasoning. The other thing is, and this is as important, is Platon's idea of a world of mathematical forms. So Platon said, okay, there are perfect mathematical forms, and they are approximations, and you find approximations of those in nature. So if you look around here, you see a lot of circles, but none of them is a really perfect circle like you would draw it in a geometry class. And Plato made a very important point, and I will sketch that later. It has very important, it's a very profound, very important point. So these were the two, in my point of view, breakthroughs, which are the fundament and the start of science. So what is this Platonic viewpoint? Let me discuss about this Platonic world of mathematical forms. You could say that is a fiction, and a lot of philosophers do that, and this is just a product of our unrestrained imaginations. And that's fine. But we scientists, we don't go into this discussion. We just say, no, this is the blueprint for what we would like to do. So we find a model for the world, or to be more precise, a model of certain aspects of the world. This model is purely mathematical. It has to be an internally consistent structure, and it is precisely defined in this purely mathematical world. And then we test this model against previous observations and carefully designed experiments. And when we find in this experimental examination that this model works, then we say this is an appropriate model which is able to describe the world or the certain aspects of that world. And the important factor is that we have, on one hand, this mathematical, these what I call Platonic mathematical world, and on the other hand, we have the experiment, and we have a certain interplay with each other. And I think I would like to sketch that by connecting three words with each other. So I have Plato's mathematical word, and in that word I have various models, and those models should describe the physical world. So I see here an interplay between them. And there is a third word, and this is what I would call, that is the mental world. And the mental world makes up that mathematical world. So what is important when we talk about science, or at least when I talk about science, then this word is true and absolute. And in this true and absolute world, you can perhaps even say this is an objective reality. Those models reside and try to describe the physical world we observe. But there's a certain problem. There's various problems with that. So these models here, they all need to be consistent, precise, and reliable. But we build this model with our own mind, which is inconsistent, not precise, and unreliable. So how does this work? How do we somehow get this reality beyond what each of us can perceive? And this is somehow, so instead of that this is the, let's say, built by one person, that is a cooperative effort. So this is something, these are aspects of reality or aspects of mathematical truth which are agreed by all. So not by one person, but agreed by everyone. And there's a problem with all, because all does not mean that everyone in the world has a say on that. First of all, the Tea Party would ruin that. All does also not mean that this is not a democratic process. Yeah, this is not to say, oh, we would like to establish that theory and we are almost done. Now we only need to talk about the lobby organization for complex numbers, and as soon as we have them under control, we have this new theory. So this is something which is really built. This is a very complex process with a sociology of its own of the scientific community. But this is how, at least I see the scientific process related to the physical world we observe, the mental world and our consciousness building together that true, absolute mathematical world. However, when I say that, I have three prejudices which I make, and that are my own choice, but a lot of persons would not agree to that. One problem is, if I say that, then I make the assumption, or I have the prejudice, that mathematics has relevance for the workings of the physical world. And of course, if you look into science, then you find that. But the problem with that is, in particular, if you have here the world of a lot of mathematical theories, the problem with that is that how can you say if a certain mathematical aspect is right now important for science or not? I mean, one of the most famous theorems is Fermat's last theorem, which has been proven 1995, but this has no relevance for physics or for chemistry or for biology. Even so, it's a very, very important aspect. So it's really hard to identify criteria to say which of those models, just from their aspects of beauty or elegance or purity, somehow have a relation to the physical world. The other problem is that here I really make this, so I really put the error in this way. I have not made it in the other way. So I somehow say that the physical world induces mentality, or I say that there is a consciousness in observing observing the world, and this is a tricky part, because it just means that the mentality is coming from the physical world. Well, we of course say, okay, our brain has a certain consciousness. We might say our cat or dog has also perhaps a certain consciousness. But we of course would not attribute that to a rock. So that is perhaps one of the mysteries built in that system. The other assumption which I make here by going to the mental world to the mathematical world is saying that mathematical truth is part of our mental activity. And this is of course because for a lot of things we are active with other things, with our own desires and other thoughts which are going on. Nonetheless, this I think is a very powerful model, and I think this explains a lot what is perhaps the core of the activities of modern science. The other aspect I would like to talk about is, I call that on my slides, more is different. Also coming from the Greeks is this idea of the reductionist ideal, and the idea to find the theory of everything. If you go to the store and you look to the latest issue of the Scientific American, you find also a picture, the theory of everything. Is the theory of everything finally there? I argue that the theory of everything, we know it. The world which we observe is dominated by electromagnetic interactions, and we can write down the theory of everything for the world we see. That is the Schrödinger equation, and we can write down what the Hamilton operator, the important part of that equation, looked like. And so we know the theory of everything, and this is perhaps a very successful product of 2,500 years of careful work. So we were able to deconstruct complex systems. We had this idea of 4 elements. 4 elements became the chemical elements. Chemical elements had a certain pattern, which is the reason of atomic physics. So that was suddenly chemistry and physics went together. And we are understanding the atoms by having a quantum theory of that. And as quantum theory, one of the key points is the Schrödinger equation, and out of that we are there. We finally can write down the theory of everything, but we cannot do anything with it. As soon as we put that together and try to build up a few more, now try to describe the system, as soon as we somehow describe more than 10 particles together, this fails. We don't have any understanding how to calculate that. None of our supercomputers, not even the one used by the NSA, are able to really calculate that. So there is not only reductionism, and reductionism is very important, because the reason why biology is now the key or the leading science is because biology adapted methods of physics, adapted reductionism, and now is very successful as a theory. But the one important point I would like to make, that there's more than only going to the small particles, and that is actually looking into the structure and the hierarchy of nature. And an example I wanted to make, I had a slide of that prepared, is a very important observation which was done in the 90s or 80s by Klaus von Klitzing and others, which was the quantum Hall effect. The quantum Hall effect got the Nobel Prize, and it allows to precisely measure the fine structure constant. The fine structure constant is this number 1/137, which David mentioned in his talk before. So this is an independent, high precision measurement of the fine structure constant. However, in order to do that, it is irrelevant how diluted or how diffuse the probe is you are doing that. There is a certain effect, it's the quantum Hall effect, which is the consequence of a symmetry. That symmetry is called localization theorem, and as a consequence of that, you see an effect or you see an emergent phenomena, and you can determine something very precisely, even so you don't need to know the internal structure of that. And this is what this is what the hierarchy of nature tells you. At each level of nature, you have important degrees of freedom, and the degrees of freedom which you would, for instance, describe the atom are not necessarily the one you would describe the probe, where you can measure the quantum Hall effect and do an extremely precise measurement of the fine structure constant. And a very simple example for that is you don't need to know the schedule of everyone here in this room to predict when tomorrow there will be traffic on the I-90 or on the Eisenhower, because there are certain ordering principles. In this case, when persons need to be at work or when kids need to be at school, and this somehow defines the traffic and is irrelevant what an individual does. And this is the important aspect when you put systems together that the bound state typically has less symmetries than the internal building blocks of that. Last but not least, so I wanted to talk about three aspects of science, and the last thing I wanted to talk about questions. So, I mean, you can ask questions, and what are well-known questions that are what, how, and why. And if we want to ask the question about what is reality and ask science about the answer, then the truth is that science tends to avoid that answer. What science tells you is how is reality. In a sense, is how do we describe the laws that govern our universe and the contents of our universe. Or if we just look to modern physics and we have the standard model of particle physics and cosmology, then we identify elementary particles and we have fundamental interactions, and the model tells you how those elementary particles interact with each other with that fundamental interactions. But they not necessarily tell you what are those elementary particles, what are those fundamental interactions, and even the most important point is science can hardly answer the question why. So it cannot tell you why there are 4 fundamental interactions, why not 5 or 3, why there's a certain number of elementary particles. So these are the limits about when we have this question about what is our road to reality, finding out about to explore nature. Then I think science has been very successful with that, very successful in finding the fundamental building blocks and getting an idea how they work with each other. And it will be perhaps in this century and with biology that we first of all now start more the understanding about complex systems and how what new fundamental theories we will find there. Similar like condensed matter in physics. So this is just all what I've probably wanted to bring up in my 20 minutes time slot. Thank you.
Mark? I'm delighted. I think I certainly didn't mean to bash the scientist's ability to see beauty, so I ask your forgiveness on that. But I'm used to scientists being Aristotelians. You know, they're not able to bridge particulars and say that it has anything to do with what Plato called universals. So it's refreshing to hear an affirmation of Plato, you know, in Plato's mathematical world, Plato's universals as something that can be appreciated by the scientific perspective. And of course that gives you the ability to see beauty. I also appreciate your comment on the limitations of science and even math to account for things in the physical world, such as not explaining, for instance, our epistemological access to understanding our past, but not knowing why we can't have the same sort of access to our future. You know, we can see our past in such a complete and experience it in somewhat of a totality, but not know what's coming. You know, not being able to kind of account for that. And I love the whole thing too of like shooting an arrow at a tree. You know, it goes half the distance, half the remaining distance, half the remaining distance, half the remaining distance, yeah, and not being able to account for why it hits the damn tree. You know, I love those kinds of conundrums if you're trying to sort of rely on math to explain, and you know, in physics to explain exactly what's happening. That, you know, I hear you saying that there's some respect for the mystery there, and some optimism that there's yet more work to be done. So thank you.
Yeah. Well, I mean, what I call prejudices or assumptions, you can also talk about mysteries in all that way.
Yeah.
Yeah. Ladies first.
Oh, okay. You were talking about you talked about you go through this series of you start out with an idea and you go through a series of tests, and if it works out, it's called an appropriate model, right, for reality. And in my experience with some members of the scientific community, and I might even say I wouldn't call them scientists, just people who are in those disciplines, I find sometimes that they take that idea of, okay, this is an appropriate model, and it becomes, it is. You know, it is this way. And I'm wondering if and I find that a very limiting idea, okay, that we can, yes, it's a model for reality, and it can give us great insight, but it's not, studying a thing is not the thing, I guess is my idea. Is there, you have much more experience with the scientific community than I do, and I'm wondering if this juxtaposition is prevalent, and do you feel it's a hindrance to further scientific inspiration and development, or I guess I'm just asking, what are your thoughts on that? Am I being clear?
You're talking about dogma?
Well, not so much dogma
Scientific dogma?
I'm talking about, maybe I am talking
Like
about
paradigms
dogma.
and narratives
Yeah,
that are used. Or
Scientific pig-headedness. It sounds
Yeah.
Well, a little bit.
confusing the map of the territory.
I have this is one of my more favorite. I have an
What?
example. I have an illustrative example. A friend of mine suffers from depression, which is of course something that has to do with the chemicals of the brain and can be treated with other chemicals, medicine. And I made the mistake of talking to him about why he might be depressed, and he's like, "It's just chemicals, Grace." Well, maybe it might just be chemicals, but I think there might. So I feel he's making an error of saying, because we know that there are chemicals involved, to say that's all it is a limiting point of view. And I'm wondering if this idea, if you find, I've found similar limitations in perception and understanding with other people I've talked to who are scientifically bent.
Well, sometimes the limitation is also powerful because it allows you to do something. So, I mean, I think this is the perspective I try to adapt later by saying more is different. So nobody would argue that you find the music in the components of your radio. And I think just nobody yet has a clear understanding about what is happening in our brain and how our brain is working. What is consciousness from a theoretical point of view? Even so, we all think we think. But I think you also have a complete, perhaps biased view on a scientific community. So I think
that's what I said.
I think the scientific community is far more lively and far more used to strong arguments and heated discussions than it looks like. Yeah, it's not a technocratic ivory tower where science shields itself. I think that is just a completely wrong point. However, you think sometimes I think persons are misusing science. Yeah, they read an article in Scientific American or in other, and suddenly they think they have found the word formula, they have found their own theory of everything. And then you somehow just have a certain skepticism on that, which perhaps can be misinterpreted as arrogance. Yeah.
Well, science has a strength and a weakness. The strength is you're building the cathedral. As the cathedral gets quite large, you have to, the additions go much more slowly because you have a lot more to test and validate against by it's moving slower. To me, the classical example is really the Michelson-Morley experiments. Speed of light was constant, and everybody just kept saying there's something wrong with the experiment, we will get it. Instead, Einstein took the opposite view, speed of light was constant, and had a great new paradigm shift in science and a relook at the physical world in terms of taking the physical experimentation for what it was worth. And so in that way, I mean, science can be, as you say, quite fluid, but it sometimes takes time for the checking, the validating, the arguments, the squabbles, the people who are defending their turf having to finally concede, because you are checking, you are then having to expand it. Because there's a heck of a lot more to that first paper that Einstein put out. There was a lot more talking with a lot more professionals, with a lot more validating of the consequences of his small theorem than really what people recognize. I mean, for years that man was talking and going through the consequences of his theory with other physicists for a very long time, which we're still going through it right now.
Well, I think this is so. Special relativity is something which is pretty established nowadays. So there's no question about that. So let me follow up on that. And I mean, first of all, yes, it's a slow process. It's 2,500 years, and this is where we are currently standing. However, one might make the argument: what progress have we made with respect to ethics compared to science? And I think, but comparing that, we had rapid developments, and we had huge improvements. And I also think that, and now I speak only about Western civilization. I don't speak about Eastern civilization. But I would argue for that science is the core of Western civilization. Our culture in nowadays is dominated.
The scientific method.
Is dominated by science and scientific thinking, and because it's the knowledge which we have gained where we have the less talked about. And I think this is pretty impressive. And I think by now making this point further, of course, science is not the only aspect of culture. I mean, you can put in religion, you can put in art, and I think all those components are important to somehow describe or somehow fulfill all aspects of human minds and human thinking. But I think science don't need to hide. I think science can be quite proud on the enormous achievements it did. And the example is a beautiful example how things work. I mean, persons thought they now have a theory which is consistent with only one missing problem, that they need to find the ether, and they did a lot of experiments like the famous Markus and Morley experiment to somehow verify the existing of the ether, and then there was no ether. And what Einstein did is he just put together works which already were done by Lorentz, Minkowski, Mach and others, and just had this, first of all, this breakthrough from connecting space and time, but also this enormous breakthrough which Mach already argued a long time before. You also find it in works of Kant that there is no absolute space. That was a huge revolution in science. So was the quantum revolution. And I think, probably your point, I think relativity is something, there are no questions asked. Special general relativity are such beautiful theories that is now all well established and well understood. The huge problem, I can argue about that later, there's no question about that. That's all rock solid. The huge problem in science is, for instance, no string theory, there's no string theory anymore, and those persons can now call themselves M theory or F theory, and they cannot even find an answer if they are now doing M theory or F theory. So that world, that huge effort, I have also my own opinion on that. But one of the huge remaining questions which haunt science is quantum mechanics. Quantum mechanics, quantum field theories has a huge problem, which is the measurement paradoxon. And that's one of the things which needs to be solved soon. And this is what one of the remaining huge problems.
Is God the answer to Schrodinger's cat?
Marcus, I think, but there was an element to your comment which I think maybe you missed, which is that it's when you have a cathedral, it's harder to change the foundation than to add a wing, right?
It is. It's hard to add. So you proceed carefully, you proceed slowly, you make sure you vet it out. Particularly when you're talking about,
And we're criticizing questioning special relativity. You're using that as an example of a time where the foundation needed to be changed rather than graft something else onto the. Right?
Yeah, but the new cathedral was built within 10 years. So.
And it's incredible, right? But there's some resistance to that. And so we have a well-established cathedral that's giant and marvelous and works so well.
There's the established theory of everyone across the world.
There's increasing resistance to changing the foundation. And so I think there was a caution in your comment.
Yeah, it's just nature. It's the nature of large group thinking. It's hard to change. It's hard to eliminate the momentum and the inertia that the current thinking has.
And I think my question relates to Frank's and Grace Mary's a little bit. This centerpiece is kind of dogma, whether it be scientific or otherwise. There's all kinds of dogma. But my question was really, what if Summerfield's fine structure constant isn't constant? How do you feel about that?
That I think will be one of the huge revolutions of physics in the next years. So what we have so far not in physics also dodged a question, or in science dodged a question, what is time? I mean, all of our works are done that we somehow get time out and just somehow regard it as a coordinate. And I think this is a very interesting point which will come particularly related to cosmology about time-dependent effect of fundamental theories. And this is important because one of the big endeavors is to find a quantum theory for gravity, and there are persons exactly, those cosmologists are exactly discussing those questions.
As much as I love listening to your German,
go on.
I have to move.